First property, closure property. Closure property of addition and closure property of multiplication. Under the closure property of addition, we got two real numbers. A is a real number as well as B is a real number. We technically say A comma B belongs to R because A is also a real number, B is also any real number. If A and B are two real numbers, suppose we add these two real numbers, then resulting number is also a real number. This property is called closure property of addition. Now, closure property of multiplication. Under this, suppose we have the two real numbers, A is a real number, B is also a real number. And suppose we multiply these two real numbers, that is A dot B, dot stand for multiplication, A dot B will also be a real number. So these properties are called closure properties. Closure property of addition in case of plus and closure property of multiplication in case of multiplying A and B. Consider real number line. On this number line, consider the two numbers. For example, A equals to -2 and B equals to -1. Now suppose we want to add A plus B, then A equals to -2 added to B -1. So -2 -1 equals to -3. A is already a real number, B is already a real number. When I added the two real numbers, I got -3. -3 is also a real number. Thus, closure property of addition tells us the addition of two real numbers is also a real number. On other hand, let us select A equals to +4 and B equals to +2. If I wish to find A plus B, then +4 added to +2 is equals to +4 +2 equals to +6. A is already a real number, B is already a real number. When we added the two real number, we got +6. +6 is also a real number. Above mathematical calculation can be easily stated as if A comma B belongs to R, then A plus B also belongs to R. This property is called closure property of addition. Consider this number line. On this number line, let us select any two numbers. Let us say A equals to -4 and B equals to -2. We have selected both negative numbers. Now -4 belongs to R. It is already a real number. B equals to -2. That is already a real number. That means A equals to -4, a real number. B is equals to -2. That is also a real number. Now suppose we multiply A, B, that is A dot B equals to -4 multiplied to -2 equals to +8. Now let us search +8 on the real number line. Yes, +8 is present on the real number line. Implies A belongs to R, B belongs to R, then A dot B also belongs to R. This property nothing but called closure property of multiplication. Let us consider one more example. Suppose A equals to plus 2 and B equals to minus 3. Here I have selected one positive number, another is negative number. Now I wish to find A dot B, that is plus 2 multiplied to minus 3 equals to minus 6. Is the minus 6 present on the real number line? Yes, minus 6 is present on the real number line. That implies A belongs to R and B belongs to R, implies A dot B belongs to R. Therefore, here also A dot B belongs to R condition is satisfied. Thus, A belongs to R, B belongs to R, A belongs to R, B belongs to R, then A dot B belongs to R. This property nothing but closure property of multiplication, and we have seen that practically how the closure property of multiplication is true for all real numbers. Suppose we got the two numbers A and B. A equals to minus 4, that belongs to real number. B equals to minus 2, that is also a real number. Suppose we add A plus B, that is minus 4 plus minus 2. If we add both the negative number, addition of negative number is always negative, so we get minus 6. And if we reverse the addition, that is a B plus A. If we reverse the order of addition, instead of A plus B, we are now adding B plus A. That is a minus 2 is added to the minus 4. Again, addition of two negative number is negative. So, in this example, what do you find? A plus B and B plus A, both answers are same. Therefore, here we can say A plus B equals to B plus A. A plus B equals to B plus A. In another example, I got A equals to plus 2, B equals to minus 3. Now A plus B equals to plus 2 added to the minus 3. So that is equal to plus 2 minus 3 equal to minus 1. Now I reverse the addition process. Instead of A plus B, I am adding B plus A, writing B first, then writing A later. Again the result is minus 1. From this one, it is clear that result of A plus B and result of B plus A are equal. Thus, if A comma B belongs to R, then A plus B always equals to B plus A. This process, this method, this idea of addition of two real number is called as commutativity of addition. Similarly, we can explain commutativity of multiplication. For that, again we are selecting any two numbers. Let us say A equals to minus 3 and B equals to plus 2. Now I am doing A dot B, that is multiplication in the order of A first, then B later, A first, then after that B. The result is minus 6. Now I am doing B dot A, reversing order of multiplication. First taking B, then taking A. Again multiplication, result is minus 6, implies A dot B equals to B dot A. This idea is nothing but commutativity of multiplication. Suppose I select other pair of numbers like A equals to plus 5, B equals to plus 2, and find out A dot B, that is 5 into 2 equals to 10. Now I find out B dot A, that is B multiplied to 5, b multiplied to 5 again 10, and I find that multiplication of a dot b and multiplication of b dot a, both results are same, hence commutativity of multiplication is true. We have proved commutativity of multiplication stands true for all real numbers. Above two discussions of commutativity of addition and multiplication technically can be stated as below. Suppose if a comma b belongs to R, then a plus b equals to b plus a. This is a technical definition of commutativity of addition. Similarly, commutativity of multiplication can be stated as if a comma b belongs to R, then a dot b equals to b dot a. These are the technical definitions of commutativity of addition and multiplication. Now I am going to explain you associativity of addition. For that I selected three numbers: a equals to -1, b equals to -2, and c equals to -3. Now let us add a plus b plus c. That is, a plus b first added -1 plus -2, then c is added -3 equals to -1 -2 plus -3 equals to -3 equals to -6. Now let us change the order of addition: a plus b plus c. So a is -1 here, added to the b plus c, that is -2 added to -3 equals to -1 -2 -3 equals to -6. We find that a plus b plus c is equals to a plus b plus c. Thus, law of associativity of addition in case of real number is true. Now let us prove associativity law for multiplication. Now select a equals to 2, b equals to 3 and c equals to 1. LHS equals to a dot b dot c, that is 2 multiplied to 3 multiplied to c, that is 1, equals to 6 multiplied to 1 equals to 6, and RHS equals to a dot b dot c equals to 2 multiplied to b dot c, that is 3 multiplied to 1 equals to 2 into 3 equal to 6. Thus LHS equals to RHS. That means associativity of multiplication is true for all real numbers. Thus associativity of addition and multiplication of real numbers can be stated as follow. If a comma b comma c belongs to R, then a plus b plus c equals to a plus b plus c. This is a technical definition for associativity of addition of real numbers. Similarly, associativity of multiplication technically can be stated as if A comma B comma C belongs to R, then A dot B dot C equals to A dot B dot C. This is a technical definition for associativity of multiplication. Since 0 lies between positive numbers and negative numbers, 0 is a part of real number. That means 0 is a member of family of real numbers. 0 belongs to real numbers. If you add 0 to any number, you are going to get the same number. Example, 2 is added to 0, you will be getting 2. Or 0 is added to the 2, then also you will get the 2. That means A plus 0 equals to 0 plus A. This is nothing but called existence of additive identity in case of real numbers. Above discussion technically can be stated as if A belongs to R and 0 belongs to R, then A plus 0 equals to A, 0 plus A equals to A. This is true for all real numbers where A belongs to R. Therefore, 0 is additive identity in case of all real numbers. Now I am going to talk about additive inverse and multiplicative inverse. I am having a number 4 and another number minus 4. Both the numbers are real numbers. If we add this number, I will get the 0. 4 is the additive inverse of minus 4. We can also say minus 4 is the additive inverse of 4 because their addition is equals to 0. So, in case of real numbers, there exists additive inverse. Similarly, if I have a number like 4 belongs to real number, then 1 upon 4 also a real number. We know that every number is a real number. 0.1, 0.2, 0.25 also a real number. If I multiply 4 into 1 upon 4, I am going to get 1. That means 4 is a multiplicative inverse of 1 upon 4 or 1 upon 4 is a multiplicative inverse of 4. Thus, in case of real numbers, additive inverse and multiplicative inverse are existing. We can technically state this idea as follows. Technical definition for additive inverse and multiplicative inverse: for every number that is A belongs to R, there is always minus A belongs to R such that addition of A and minus A equals to 0. Similarly, for multiplicative inverse, for every A belongs to R but A is not equal to 0, there is always 1 upon A belongs to R such that A into 1 upon A equals to 1. Thus, additive inverse and multiplicative inverse always present in case of real numbers. Now, the last property, if A comma B comma C belongs to R, then A dot B plus C equals to A dot B plus A dot C. In this property, there is multiplication as well as the addition are getting distributing over the addition. That is, multiplication distribute over addition for all real numbers. This is true for all real numbers.